welcome to go.
Yeah.
Welcome to Coffee with Caleffi. My name is Max Rohr. I'm the Director of Education and Technical Marketing. Today I'm joined by Hailey Mick, and thanks for bearing through the technical difficulties with the audio here. So go ahead and advance to the next slide. We'll go through these really quickly. If you have issues with audio, don't call us. We don't know how to fix it either. Log out and log back in. We do have copies of the presentation. We can get that to you with the post survey, and we'll have this on YouTube as well. Okay, go ahead. Then this is what the certificate of attendance looks like. We'll send those after the webinar for people who attended. Okay, Hydronics 33 is out and should have arrived at your house or office. If you subscribe to get hard copies, it's also available on the next slide with hydronics.caleffi.com. You can always get either a PDF or an interactive digital version, so that's up now as well. We don't have a Coffee with Caleffi in January because we will be at the AHR show. So come see us live. We're going to have Coffee with Caleffi in the booth. So we'll have a few different panel discussions. I think on the next slide, it shows the different lineup. So we'll have Mechanical Hub doing kind of a kickoff event with us. We're going to be talking about heat pumps with John Siegenthaler and Justin Job from Enertech. And then we're also going to have just an incredible panel of Carlson Houlihan Award winners that we're going to interview with some of the next gen all-stars. So kind of bridging the peak of the industry with some of the new people on the scene as far as a conversation about education goes there. Then, okay, Hailey, now I need to find your bio. Got lost in the shuffle. Okay, so let's see. Hailey is great, and we're happy to have her. Okay, so she is an engineering business development manager at Uponor North America. She has 17 years of experience in the commercial HVAC industry, including engineering applications, technical sales management, hydronic training management, product engineering, and sales engineering. She is passionate about educating customers on product functionality and selection, design improvements, and sustainability, while also providing guidance, helping industry professionals solve problems. She holds a Bachelor of Chemical Engineering from Auburn University and is a member of ASHRAE, ASHE, ASPE, and the Uponor Sustainability Core Team. So welcome, Hailey. Thanks for being our guest and working through the GoToWebinar audio issues with us. I'm going to mute myself and turn my camera off in case I was part of the problem, and I'll turn it over to you. We'll take questions at the end, so just go right through the slides and I'll kind of keep track of some things that come up as we go, and we'll ask them at the very end.
Okay, wonderful. All right, so thanks again for bearing with us through those technical issues. I swear we practiced and something went wrong this morning, but here's a look at our agenda for today. We are going to cover a lot of information in this hour, and as you can tell already from my accent, I am from the South, which means I need to talk much faster than I normally do, but I do think all this information is very important. So as you can see on the screen, we're going to talk about the differences between systems that are out there being designed and used today that are considered highly efficient. We're going to look at water-based and refrigerant-based systems, briefly discuss the differences between a central plant versus a decentralized plant, review the three heat transfer methods and go over several definitions, create a system evaluation, and share some resources available to help you with design decisions, and hopefully wrap up with a brief Q&A session, but you'll have my contact information to continue the conversation further if you need to do so. All right, so before we get started, I think it's really important to just remind everyone why we care to begin with. And the reality that we're currently facing is that between now and 2050, the world's population is expected to increase by 1.9 billion people, at which point 7 billion people are expected to live in urban areas. So to support this growth, it is estimated that some version of New York City is being built somewhere around the world, roughly every 34 days for the next 37 years. And it's truly amazing to look back and see what we have done in the last 50 years. But can you imagine where we will be 50 years from now? Are you prepared to summon an unmanned electric flying taxi? This is not as futuristic as you might think. Just last month, in November of 2023, Volocopter, the pioneer of urban air mobility, completed its first flight test at the downtown Manhattan heliport in New York City. Volocopter has now successfully and safely conducted flights in the heart of two of the busiest metropolitan hubs of the world, New York City, and Singapore. And like it or not, change is inevitable. And right now, the construction industry is under massive pressure to make a lot of changes. The built environment generates an estimated 40% of annual global CO2 emissions, and decarbonizing our buildings is a critical step to meeting global climate goals. The Sustainable Development Goals, or SDGs, emerged from rigorous research into global conditions and trends and provide a blueprint to achieve a better, more sustainable future for all. The 17 goals are all interconnected, and in order to leave no one behind, it is important that we achieve them all by 2030. So let's get started with the actual presentation by discussing some system definitions and differences. I think it's probably safe to assume that everyone here today is in some way, shape, or form involved in constructing buildings. We build buildings to protect us from the elements, to protect us from extreme temperatures, to keep us safe, and to keep us comfortable. And in HVAC, our primary goal is relatively simple: to balance the heat gains and losses through the building envelope, along with internal heat gains, to maintain consistent, comfortable indoor spaces. And this could be as simple as a fire pit in the middle of a primitive structure. But for the commercial applications that we're talking about today, we use engineered system solutions, from unitary rooftop equipment to complete hydronic systems with cooling towers, boilers, chillers, and pumps. These systems heat and cool interior spaces primarily by conditioning the temperature of the discharge air from the air handling unit. Essentially, we heat and cool by blowing tempered air. And this, of course, is convective heat transfer, more specifically forced convection. But there are other ways to transfer heat. We know that there are three modes of heat transfer: convection, conduction, and radiation. Convection, as we just discussed, is heat transfer through the movement of molecules, or specifically air. Conduction is heat transfer through direct contact between two bodies at different temperatures, and radiation is heat transfer through electromagnetic waves. So the first thing we want to discuss is an air-based system and what we mean by central versus decentralized design. And what we're really talking about here is where in the building is the heat exchange happening between the air and the coil that is carrying the heat transfer medium. Is that happening in a central plant where the air is conditioned and then distributed to your zones through ductwork, which is sometimes called an air side or a forced air system? Or are we piping water or refrigerant to the zone and then having that exchange happen on a local level? So regardless of which option has been chosen, the goal is to heat the air, cool the air, and address humidity in the air by means of having the air come in contact with a hydronic or DX coil. And whether you are using an air distribution model with conditioned air being delivered to zones through ductwork, or a hydronic or refrigerant-based distribution model, we still need to address ventilation. Ventilation is about providing fresh air and dealing with toxins that might be building up in the space. If you have a decentralized design in most large commercial applications today, you're still going to have some amount of ductwork to deliver that ventilation, and you will have a dedicated outdoor air system. Central forced air systems often attempt to handle both comfort and ventilation simultaneously, whereas a decentralized system tends to use separate dedicated systems to address comfort and ventilation. ASHRAE even addresses these two systems with two different standards. We have standard 55 for thermal comfort and standard 62.1 for ventilation. Because there are so many variables that need to be addressed for thermal comfort and so many other variables that need to be addressed for ventilation, building these central station air handlers can become quite cumbersome and difficult to properly select rather quickly. Furthermore, the operation of these units becomes quite complex and sets us up for a system that has no choice but to use more energy than necessary. Temperature, humidity, contaminants, and oxygen levels do not fluctuate in proportion to one another, and thermostats and sensors need to monitor each of these details and react accordingly. If the temperature is sufficient but the CO2 levels are high, then the central air handling unit controlling it all must turn on, bring in, and condition outside air, which in turn will have an impact on the space temperature. Conversely, if we keep these systems separate, then the heating and cooling equipment can now focus solely on comfort. It can do what it does and do so well. And a separate ventilation system can do what it does and do so well without overtaxing either system. Central systems tend to be more expensive to install, more expensive to operate, and fail faster than decentralized systems. And when they fail, the entire building is down versus a zone having a failure in a decentralized system. Lastly, it takes significantly more energy to move air than it does to move water. So for the purpose of this presentation and the system evaluation that we're going to walk through, we're going to make the assumption that comfort and ventilation will be handled separately, and we're going to continue down our path of comparison by discussing the heat transfer medium options. Water versus refrigerant. Again, we have several options when it comes to our HVAC systems in commercial construction today, and frankly, there are not set rules for when to use which. It's often a function of building space, location, purpose, budget, timeline, engineer or owner preference, or even the goals of the project itself. The concept behind the design options here are similar in that they both distribute fluid to a zone to condition the air locally, but the amount of refrigerant needed in the hydronic system is negligible and is typically contained compared to a VRF system, which sends refrigerant-filled piping all throughout the building. And it's hard to dispute the fact that minimizing the volume of refrigerant being used minimizes our greenhouse gas emissions. Global warming potential, or GWP, is a measure of how destructive a climate pollutant is. The GWP of a gas refers to the total contribution of global warming resulting from the emission of 1 unit of that gas relative to 1 unit of the reference gas, carbon dioxide, which has been assigned a value of 1. Refrigerants today are often thousands of times more polluting than carbon dioxide. And the two most common refrigerants currently being used are R134A and R410A, which have a GWP of 1430 and 2088 respectively. Meanwhile, water has a GWP of 0. Granted, there is research currently underway for refrigerants with much lower GWPs, but today these are the choices available. And while instances of refrigerant leakage are few, the risks posed by VRF systems are nonetheless concerning. VRF systems have hundreds, if not thousands, of feet of piping filled with hundreds of pounds of pressurized refrigerant. At the very least, it is important to note that when the decision is made to use a refrigerant-based system like a VRF system, there are several additional safety measures that need to be put into place to prevent further harm to the occupants and the environment per ASHRAE standards 15, 34, and 147. So let's discuss VRF just a bit further to make sure we all understand what we're talking about with this system. So what is VRF? VRF, or variable refrigerant flow, also sometimes called variable refrigerant volume, is a system that uses refrigerant as the working fluid to distribute heat within a building. VRF was first developed in Japan in the 1980s and started appearing on the North American market in the early 2000s. System output is regulated based on system load, and the refrigerant flow is regulated by electronic expansion valves and variable speed compressors. In general, VRF systems consist of a central outdoor unit, water-cooled or air-cooled, and multiple indoor units of different types and capacities. And here we see a general representation of a hydronic distribution design, which is sort of similar to VRF designs, only it uses water rather than refrigerant as the heat transfer medium. So this design would have a water-cooled or air-cooled chiller and a boiler or heat pump, something along those lines as the heat source. Now, radiant heating and cooling is a bit different than what we have seen so far, but it has been used for centuries around the world. You look at the Roman hypothos, for example, where they would circulate hot flue gases underneath the raised floor slabs, and this hot gas would increase the floor temperature and create a warm, comforting environment by taking advantage of the thermal mass of the floor to really hold on to that heat. And here we have the Korean Ondol system, a system where they also use those hot flue gases from the stove or the oven and circulate it through the underside of the floor before exhausting the gas through the chimney on the other side of the building to capture that heat and warm the thermal mass of the space. And here we see photos from Seoul, Korea. So these are the openings where they would put their wood, which is the fuel for the fire. And again, the gases are discharged to the chimney after passing underneath the raised floor. So as you can imagine, this is very effective at creating a comfortable, inviting space. You do get some conductive heat transfer through the contact between your feet and the floor, but most of the heat transfer is through radiation heat transfer, where we're taking advantage of the thermal mass of the floor. And that's really how radiant systems work. So we think about the conventional design process. The architect designs the building envelope, the walls, floors, and ceilings, and then the engineer calculates the heat gains and losses, both internal and external, based on the architectural design, and then designs an appropriately sized HVAC system to offset those gains and losses. Well, radiant systems are really the beautiful integration of architecture and sustainable HVAC design, where we're using the architectural elements to maintain comfortable spaces. And we see this approach used in small residential projects all the way up to large commercial projects like the Bangkok Airport in Thailand. And here we see the Academy of Sciences building in San Francisco, California. Now, with contemporary radiant heating and cooling systems, we don't circulate hot flue gases underneath the floor like they did in Europe or Asia. We circulate water. We circulate chilled water or heating hot water, depending on the mode of operation, through a network of PEX tubing embedded in the concrete slab. And by simply controlling the flow and temperature of the water that we're circulating, we can control the temperature of the slab and therefore drive heat transfer in one direction or another. When we circulate heating hot water, we're using the slab to radiate heat. And when we circulate chilled water, we're using the slab to absorb heat. So the PEX tubing is routed in the concrete slab, and then it comes up to the manifolds, which you can see on the right-hand side. And this is where we make our chilled water and heating hot water connections. And one of the questions that we frequently get asked is, when we're heating the space, it makes sense to heat the floor. But when we're cooling, don't we have to cool from the ceiling because heat rises, right? Well, actually, heat does not rise. Hot air rises due to buoyancy based on the differences in density. So if heat does not rise, per se, what direction does it go? And to answer this question, we simply have to go back to our good friend, the second law of thermodynamics, or more specifically, the second formulation of the second law, which states that heat will always naturally go, unless work is being done to it, from a high state to a low state, or for us, from hot to cold. And intuitively, we understand that, right? If we grab a hot coffee cup, the heat from the cup will transfer from the cup to your hand. But if you grab a cold glass, the heat from your hand will actually be transferred from your hand to the cup, leaving you with a feeling of being cold. So it doesn't really matter if we're conditioning the floor or the wall or the ceiling, as long as there's a temperature difference or a delta T between the controlled surface and the object or the people within the space, you're always going to get heat transfer. And we're able to use this to create very comfortable spaces. If you look at the way the human body exchanges heat energy with the space around it, you see that almost half of it is through radiation heat transfer. So it makes sense that systems that rely on radiation heat transfer are more conducive to human thermal comfort. You can almost think of your skin as a radiant surface where you're constantly exchanging energy with the space around you. And the rate at which this energy either leaves or enters your body is based on the delta T between the space temperature and your skin surface temperature, leaving you with a sensation of feeling either hot or cold. So now that we've talked about some systems, let's discuss a few definitions. For starters, what are we actually referring to when we say net zero? Is it energy and electricity or carbon and emissions? Is one more important than the other, or do they both matter? The answer is yes. We cannot get to one without the other. Our goal is to get to net zero carbon, but we must minimize the energy that we're using and change to clean energy sources in order to achieve this goal. Decarbonization refers to the goal of ending our dependence on oil and gas as power sources to reduce the carbon dioxide emissions that raise global temperatures. Electrification refers to using technologies such as vehicles or heat pumps that operate with electricity instead of burning fossil fuels such as oil, gas, and coal. Electricity generated through clean resources such as wind and solar is considered a decarbonization strategy. And in order to reach net zero, emissions from our commercial buildings will need to be reduced and balanced. And there are many schemes that help offset carbon through planting trees or using technology like carbon capture and storage. But we have to start the process with intentional designs that use clean energy sources, maximize energy efficiency, minimize transportation costs, and conserve our most precious resource, which is water. From the ASHRAE position document on building decarbonization, we can read that ASHRAE's position is that decarbonization of buildings and their systems must be based on a holistic analysis including healthy, safe, and comfortable environments, energy efficiency, environmental impact, sustainability, operational security, and economics. What it boils down to is this. We need to have a comprehensive approach that addresses every stage of a building's life cycle: design, construction, operation, occupancy, and decommissioning. The main contributors to greenhouse gas emissions include construction processes, energy consumption, methane emissions, and refrigerant use. A thorough life cycle assessment must account for both operational and embodied emissions. Operational carbon is the amount of carbon emitted during the operation of a building. This includes both energy and water-related emissions. Embodied carbon is the amount of carbon emitted from the extraction of raw materials for the building to the building's end of life, including refrigerant emissions. It's everything in the life of the building that's not covered by operational carbon. Operational emissions stem largely from energy use during the building's functional lifespan. In contrast, embodied emissions cover the greenhouse gases emitted from the raw material extraction to manufacturing, transport, and installation of the building components. These emissions also extend to the building's maintenance, repair, and eventual decommissioning, including refrigerant leakages throughout its life cycle. We really need to start thinking and talking about whole life carbon, not just for our buildings and the architectural building materials, but also specifically about MEP equipment. Early incorporation of design elements aimed at carbon reduction needs to be a priority. Assessing the building's life cycle emissions during the design phase enables designers to make data-driven decisions that minimize long-term GHG emissions. MEP systems are made largely from high embodied carbon metals, for instance, aluminum for motors, copper for piping, and steel for enclosures and support rails. And due to the low recyclability of most of these equipment types, virgin metals need to be mined, treated, processed, and transported over long distances, a highly energy-intensive endeavor to create new equipment at the end of its short, useful life. So keeping in mind everything we just discussed, how can we take the knowledge that we have and start the process of moving in the right direction? And the answer is by making a comparison through a system evaluation. So again, we're going to attempt to create an apples-to-apples comparison where we're going to assume that ventilation is being handled through a dedicated system, and we're going to look at this short list of things that we just saw in the ASHRAE position document that I believe we can act easily on today. So through the next several slides, we're going to evaluate a VRF system, a fan coil system, and a radiant system, and compare the impacts on health and safety, occupant comfort, energy efficiency, embodied carbon, and economics to see how they stack up against each other. And then at the end, we'll revisit this table for a final score. So I've already sort of mentioned this, but you're going to quickly notice that for each of these categories, there's a lot of similarities between a VRF design and a hydronic fan coil design. But the biggest difference is, of course, the heat transfer medium. Generally speaking, these systems have a central plant generating hot or cold fluid or gas, hydronic or DX, and then distributing that heat transfer medium to a zone where the air is then circulated over a coil to be conditioned. And inherent to this design is the need to constantly move the air around in the space. Unfortunately, that means all the dust, germs, and are also constantly moving with a VRF and a hydronic fan coil design. When air is constantly being moved, it's difficult to clean our spaces. And while this is an adorable picture of a happy child, it's also a bit gross to think of all the things that are being inhaled. Now, on the other hand, you might say if the air is constantly being returned to a fan coil or a cassette, then it's constantly being filtered and cleaned. But let's be honest, changing out filters is most likely not happening as often as it should. And ultra-high levels of filtration come at a premium price and significantly increase the airside pressure drop and energy required to move that air across the coil. Hydronic radiant systems provide improved air quality by allowing the particles in the air to settle so they can be removed through cleaning of the surfaces. The only air being moved with a hydronic radiant system is the fresh ventilation air, which is being filtered at a single location that is more likely to be regularly monitored and maintained. With radiant systems, maintenance is really simplified, primarily requiring visual checks. And whether we want to admit it or not, refrigerant leaks. I know I have personally noticed the temperature in my home feeling warmer than expected, made my way to my outdoor unit, and found something that looked like this. And while there are a handful of reasons this could occur, it is typically due to a refrigerant leak. It is possible for a leak to develop in a hydronic system or a VRF system, but a leak in a hydronic system is generally easy to detect, and the material leaking is typically water or a mixture of water and antifreeze. And well-designed hydronic systems provide numerous isolation valves that allow the portion of the system where the leak is to be isolated from the remaining parts of the system. Hydronic systems that distribute heating and cooling energy produced by a refrigerant-based source can be designed so that the refrigerant-containing devices can be confined to a mechanical room or located outside the building. A VRF system leak is a serious issue due to the large refrigerant volume it contains. A single leak can result in a complete refrigerant loss and even require building evacuation and intervention of hazmat teams. R410A and similar refrigerants can displace the air in a room. In spaces with minimal ventilation, it is possible for refrigerant concentrations to reach values that could render occupants unconscious and ultimately lead to suffocation. For this reason, ASHRAE Standard 15 limits refrigerant volume based on the smallest space served. Those people designing VRF systems should verify that the amount of refrigerant that could be lost due to a leak and the smallest space into which this refrigerant could accumulate are in compliance with this standard. Properly addressing the risk of refrigerant leakage requires extensive design considerations and added costs, such as refrigerant detectors, separate systems for smaller spaces, piping, rearrangement, etc. At the end of the day, worst case, refrigerant could build up in the building and lead to asphyxiation. Best case, it gets out of the enclosure and does damage to the environment. So based on the minimal air movement and ensuing ability to clean surfaces easily, the minimal amount of maintenance required, and lack of excessive amounts of refrigerants used, hydronic radiant systems check the box as the best option for health and safety, and radiant systems come out on top. Now on to occupant comfort, which is generally measured by IEQ, or Indoor Environmental Quality. IEQ is a broader term that encompasses AQ, or indoor air quality, and other physical and psychological aspects of the indoor environment. IEQ plays a key role in the design of high-performance green buildings. Starting with sound. With a VRF or fan coil unit design, the space temperature fluctuates. That's actually what controls the operation of the fan and motor in the zone. And I'm sure you have all experienced those nonstop temperature swing in office spaces and subsequently the nonstop sound of the fan turning on and off and back on again. We hear it so much we're almost accustomed to it now. The noise from most VRF and fan coil units is in the range of 50 to 70 decibels when they're running. And this is not a harmful level, but it is certainly annoying and distracting. And on to odor. As temperatures have been dropping across North America, people everywhere are turning on the heat in their homes and offices for the first time this year. And they are also all likely experiencing a very familiar smell, the burning off of the dust and so many other things that I will refrain from mentioning that has accumulated on the coil. Again, when the air is constantly moving, it's difficult to truly clean the space. Now, when it comes to thermal human comfort, the standard that our industry uses is ASHRAE Standard 55. And if you go through ASHRAE Standard 55, you'll see that there are 6 different factors that impact human comfort. Now, as system designers, we really don't have much control over things like clothing or metabolism. So we're left with 4 factors where we can really make an impact: air movement, air temperature, indoor relative humidity, and radiant temperature. Now, most of us understand how air movement can impact comfort, and we certainly all understand how air temperature and indoor relative humidity can impact it, but what is radiant temperature, and how does it differ from air temperature? To understand the concept of radiant temperature, let's consider an example. Take the room that you're in right now. Let's say that we're radiantly cooling the floor surface. So we're controlling the surface temperature of the floor, but all other surfaces like the walls, windows, and ceiling are going to be uncontrolled. If we take the area-weighted average of the uncontrolled surface temperature, we would get the average uncontrolled surface temperature. Now, if we were to take the area-weighted average of the average uncontrolled surface temperature and the controlled surface temperature, so in this case the floor, then we would get an approximation for the mean radiant temperature. And that is a term that you are all probably familiar with, especially if you have gone through ASHRAE Standard 55. But let's take it one step further. If you were to take an average of the mean radiant temperature and the space temperature you would get an approximation for what is called the operative temperature. This is important because when you go through ASHRAE Standard 55 and you look at the PMV and PPD curves, you know that the temperature they're referencing is the operative temperature, not the space temperature. That's because the operative temperature can be thought of as the temperature you actually feel, which can be different from the space temperature that you measure. Let's say you were outside on a sunny January day in New York. It's cold outside, but the sun is shining, so you actually don't feel too bad. However, the moment you step into the shade, you will feel much colder. Air temperature would be the exact same, but because you're not getting that radiant energy from the sun, you're going to feel much cooler. So to further illustrate this, let's put some numbers on our example. So if we're controlling the floor surface temperature in cooling mode, we would have it at around 66 degrees, but the rest of the surfaces, again, in this example, are uncontrolled. So let's say the walls here are 76 degrees, the ceiling is around 78 degrees, and the window is at 80 degrees. So if we take the area weighted averages, we can approximate the average uncontrolled surface temperature as 78 degrees, and the mean radiant temperature at 72 degrees. So with a room temperature of 78 degrees, we would have an operative temperature of 75 degrees. Now, what does this mean? It means that even though the room temperature is up to 78 degrees, the occupants in the room actually feel like it's only 75 degrees. And when we can operate a cooling system at a higher temperature, we can achieve significant energy savings. And here's a perfect example of just that. This is the Crystals Mall, which is part of the MGM Grand City Center right on the famous Las Vegas Strip. And while you may know the building, what you may not know is that all the open spaces within the mall are radiantly cooled. And several years ago, we took a group of engineers to this mall so that they could get a sense for what a radiantly cooled building felt like. We stopped in this big open area and asked them how they felt. They all agreed they felt fine, very comfortable. Then we asked them to guess what the temperature was. The first engineer said around 72 degrees, the next one said 75, the next said 74, and so on. So to summarize, everyone felt comfortable, and they all agreed the temperature was probably around 74 degrees. We then pulled out a temperature sensor, and it was 79 degrees in the space. Now, you would never imagine that an occupant would feel comfortable at 79 degrees, and you would certainly never set your set point to 79 degrees with a forced air HVAC system in cooling mode. But in this case, because of the radiantly cooled floor, which was around 66 degrees, they all felt like it was about 74 degrees in the space. Think about the energy savings that the facility manager can realize when they don't have to manage a 75-degree space, but instead they can set the set point as high as 79 degrees. With a radiant floor, we typically see cooling space set points of 78 degrees and heating set points of 68 degrees. Thermal comfort and the lack of temperature swings is a major benefit of a radiant heating and cooling system. Remember, a large portion of our body's heat loss is by radiation to cooler surfaces surrounding us. The cooler these surfaces are, the faster they will pull heat from us and the more uncomfortable we will feel. But by warming these interior surfaces of floors, walls, ceilings, and windows, radiant heating reduces radiant heat loss from our body. The familiar but uncomfortable situation of warm air blanketing the ceiling while cool air pools at the floor level is eliminated with radiant solutions. Not only does this improve comfort, it reduces heat transfer through the ceiling and upper portions of the wall, making radiant cooling highly efficient. The greater the height of the interior space, the more beneficial this characteristic is. The need for fans to push the warm air back down to the occupied zone of the room is eliminated in most cases when radiant heating and cooling systems are installed. Another benefit with radiant floor cooling is the ability to deal with high direct solar heat gain. Take a look at this photo. Have you ever had to design a space like this? You can just imagine that if you ran your load calculations and sized your CFM based on the room sensible here, then this space might feel like a wind tunnel. But they are able to effectively deal with this high direct solar heat gain because they have a radiantly cooled floor surface. You see what's happening here is that you have the shortwave radiation of the sun coming through the fenestration, and when it hits the floor surface, two things occur. Part of the energy gets absorbed into the floor based on the absorptivity of the floor surface. And the rest of the energy gets converted into long wave radiation and is reflected back into the space. And it's this reflected energy that warms up the objects and bodies within the space. So if we're actively cooling the floor surface, then we can absorb a much greater percentage of that energy before it gets reflected into the space. And that's why you see so many radiant floors in areas with a lot of glazing. It can be the perfect solution to a very tricky problem. Now for humidity, you always need to look at the dew point. I've heard many engineers express concern about radiant cooling in humid environments. And as it turns out, you can, in fact, design radiant cooling in humid environments because it really doesn't matter how humid it is outside. All that matters is how humid it is inside. And that's what mechanical engineers do for a living. Regardless of whether or not a radiant system is being used, their job is to manage the indoor relative humidity within that range of about 30 to 60% per ASHRAE standard 55. If that is done effectively, condensation will not be an issue. A hydronic radiant cooling system, however, can only address the sensible loads. The latent load will need to be handled by the dedicated outdoor air unit. Let's take a standard room design at 75 degrees and 50% relative humidity, and now find what the dew point would be. So you're going to pull out your psych chart, which if you don't have one handy, there's an app for that. You're simply going to draw a vertical line from the bottom of the chart to the saturation curve at your desired dry bulb setting. Then you're going to find your desired relative humidity curve and trace that line. Mark a point where those two intersect, and then draw a horizontal line from that point to the saturation curve. This is the dew point at your desired dry bulb and relative humidity. So the dew point in this example would be 55 to 56 degrees. And if we push that room temperature to 78 degrees, like we just mentioned is the case for a lot of cooling systems at relative humidity of 50%, then the dew point is going to creep up to 58 degrees. So what does that mean? That means that any surface in the space that is below 58 degrees is at risk for surface condensation. Therefore, we simply keep the surface temperature above the dew point and we will not have a problem. As long as the system is operating properly, we will never be at risk for condensation. A conservative approach is to control supply water temperature at or slightly above the dew point. This will guarantee that your slab will never reach dew point. This leads us to our last topic in this section, which is design flexibility. The built environment should be able to change to meet shifting needs, whether social or environmental. Flexible architecture considers how occupants' needs may change and requires us to design spaces with those changes in mind. Theoretically, this reduces the need for redesigns, especially in our MEP system. As the world changes and occupant needs evolve at a faster pace than we have ever seen, the built environment must be designed in consideration of these future changes. When radiant heating and cooling is used to condition the space, the opportunity to reconfigure the space is truly optimized. Now for the ranking in this category. So due to the fact that both VRF and fan coil systems essentially require temperature fluctuations to operate, and we know that humans recognize temperature variances as small as 1 degree, we're giving these two sort of a half a point in this category because despite that fluctuation, they do a decent job of maintaining the space temperature, albeit very inefficiently. That being said, both VRF and fan coil systems score higher than a radiant system for humidity. While humidity is not an issue with a radiant system, which is properly designed and operating as expected, a radiant system cannot dehumidify the air at all. However, radiant heating and cooling systems are certainly the better solution for noise and odor mitigation as well as design flexibility. Now onto energy efficiency, where we're going to focus on the distribution side of the system. Several studies throughout the years, like this one from IAPMO, have shown that the farther the piping distance, the less efficient a refrigerant-based system becomes. Although proponents of VRF systems point out that no circulators are needed to move refrigerant through a building, electrical energy is required just to move refrigerant gas and liquid through piping. That energy is supplied as electrical input to the system's compressors. The electrical energy consumption for moving refrigerant through a VRF system per unit of heating and cooling energy delivered is significantly higher than that required for a well-designed hydronic system. The graph we see here compares the energy required to move the cooling medium through a building. And the VRF system uses about 6% per 100 foot of refrigerant line set, compared to the hydronic system, which uses only about 0.3% per 100 foot of distribution distance. So as you can see, the more piping that is required, the more difficult it becomes to justify a refrigerant-based system over a hydronic system from an energy consumption standpoint. Furthermore, studies have shown that many VRF systems are conservatively measured at 50% below published energy efficiencies. The reason is simple. A real building requires multiple D rates to the rated efficiency based on actual operation. Variables in a real building include outdoor air temperature, length of refrigerant lines, elevation change between condensing unit and indoor split units, indoor room temperature when cycling, actual airflow, constant versus variable room loads, and multiple other real-world operating differences from prescribed laboratory test points. Even oil migration in the refrigerant charge affects efficiency in reality. When VRF systems are lab tested to find published IEERs, a 12.5-foot separation between the indoor unit and the outdoor unit is used. In a real building, there's likely to be hundreds of feet of copper refrigerant line installed. And as we just saw, for refrigerant, distance is the #1 energy hog. For maximum efficiency, water is the best option. This is a study that was done by Lawrence Berkeley National Labs comparing a conventional VAV system with a radiant system coupled with a dedicated outdoor air system. And they found that by using radiant systems, depending on the climate zone, they could save anywhere from 17 to 42% over the baseline VAV system. And if you look at the graph, you can see that a lot of the savings comes from the fact that we can generally reduce the amount of air that we're moving by using water to move those BTUs instead. Essentially, we're replacing fan motor horsepower with pump motor horsepower, but we all know that the heat transfer capacity of water is so much greater than that of air. So we can move those BTUs much more efficiently. And we've seen subsequent studies that show that radiant systems can save over 50% versus the baseline. And so we've seen radiant systems employed in projects such as the Carl R. Darnell Army Medical Center at Fort Hood in Texas, a LEED Gold project, the Cleveland Clinic, a LEED Silver project, the Bangkok Airport in Thailand with over 30% energy savings, and Manitoba Hydro Place, which is LEED Platinum and was recognized at the time of completion as the most energy efficient office building in North America. NREL's Research Support Facility and the David Brower Center both LEED Platinum. And while designing a radiant system does not mean you will automatically receive that rating on your building, these are examples of when, posed with that challenge, the design team chose to incorporate radiant heating and cooling as part of an energy efficient design strategy to get the highest rating achievable by the USGBC. And nothing demonstrates versatility of a hydronic system like the ability to integrate green technology. From mild to wild, there is very little that an innovative designer cannot create. Hydronic systems can efficiently utilize various energy sources like geothermal and solar energy for everything from space heating and cooling to snow melting and hot water supply. And here is an example of just that. With radiant cooling systems, again, our water temperatures are somewhere between 55 and 58 degrees, which means maybe you don't need that chiller supplying 42-degree water. This project is an interactive science museum in San Francisco where the engineering team on the project designed an in-slab radiant cooling system, and based on their loads and the slab configuration, they calculated that they needed around 58 degrees supply water, and they get that water right out of the San Francisco Bay to get very close to free cooling about 9 months out of the year. Thermal energy storage, or TES, is a versatile technology that stores heat and cold for later use and is ideal for hydronic systems. It saves energy and cost by producing hot or cold water during off-peak times, a practice known as load shifting. And load shifting involves adjusting energy consumption patterns to use energy during low demand periods, helping us to maintain a stable energy grid. In the category of energy efficiency, hydronic-based radiant systems are still the clear winner. Moving on to embodied carbon. When using a refrigerant-based design, metallic piping is the only option that is acceptable. But when hydronic-based systems are chosen, you have the option of using polymer piping solutions. The US EPA has defined life cycle assessment, or LCA, as a comprehensive method for measuring environmental impacts associated with the product's life cycle. And studies have shown that when compared to copper, the production of PEX uses 42% less CO2 emissions, and that PEX has 47% less embodied carbon than copper. And similar studies are well underway for PPRCT for larger diameter systems, and results are in alignment with what we have historically seen with PEX. Design concepts that incorporate environmentally responsible materials and avoid potential contaminants are the standard that we should be building towards. Additionally, polymer solutions can be up to 80% lighter than copper or steel, and there's a direct relationship between the product and a reduction in transportation costs and emissions. They're also easier, faster, and safer to install than metallic solutions. And because polymers outlive metallic solutions with life expectancies of 50 to 100 years, you've reduced the need for replacement. This is another benefit for not only the owners of the building, but the environment as well. To make real progress toward a more sustainable construction industry, transparency about the products that we're using is required. Environmental Product Declarations, or EPDs, use LCA calculations to comprehensively evaluate a product's environmental impact along its entire life cycle. These are official declarations that contain comprehensive information about our product's environmental impact, and they allow engineers to influence the carbon footprint of buildings and projects by selecting the most sustainable solutions. So along with high embodied carbon material for both the equipment and the piping system needed to be used, VRF systems have a shorter life expectancy. Hydronic systems have been known to last 25 years or more. VRF systems are more difficult to install, have more components, and they're heavier to transport. So once again, hydronic radiant systems are the real winner in this category. Let's wrap up our evaluation with economics, where VRF system designs have unique strengths and benefits for buildings and spaces of particular sizes. Many of the industry claims of cost savings relative to other industry standard systems are based on antiquated comparisons that just simply do not hold up to careful review. In this study commissioned by Xylem that evaluated HVAC systems in a number of South Carolina school buildings, hydronic systems outperformed all other systems, including VRF, in terms of lower energy use, cost, and life expectancy by as much as 24%. The initial cost of a hydronic system is generally lower, and systems offer a much wider range of flexibility for components, operation, and maintenance, both in terms of parts and in terms of service. In October of this year, I was fortunate to be able to attend ASHRAE's inaugural decarbonization conference for the built environment in Washington, D.C., and participate in a session on radiant heating and cooling. So the next few slides that I'm going to be showing today are from that session where McPherson Engineering delivered the results of radiant heating and cooling projects that they designed. In this particular example, this is real data for a school in Saskatchewan that just opened to students this fall. And McPherson initially recommended radiant heating and cooling. Unfortunately, the school district opted to go with heating only, but the numbers are certainly still valid. Ultimately, what got installed was a radiant floor heating system with 2 large custom VAV air handlers for cooling and ventilation, and construction costs for the building came in around $470 per square foot. So taking a look at the heating side of things first, the standard option for what is considered a high efficiency design in that market is a baseboard heating solution. So that's what was priced as the baseline here. So as you can see, the baseboard solution was going to require 950 linear feet of baseboard heating and would have an installed cost of around $148 per linear foot. And the radiant solution would require approximately 22,000 square feet to be heated and cooled, and the installation cost there was expected to be around $4 per square foot. And one thing to note here is that the radiant solution does include additional manifolds and piping for cooling, because that's what they're proposing, even though that did not ultimately get installed. So had they rerun these numbers for heating only, the installed cost would have probably been closer to $3 per square foot. So the numbers that I'm about to show you are very conservative. So this is what the differences would have looked like had the radiant heating and cooling been installed. So that alone is just over $52,000 in savings. And looking at the cooling and ventilation side of things a little bit, they did decide to go with forced air, and that required 2 pretty substantial custom air handlers variable speed supply and return, exhaust fans, dual streams with heat recovery, etc. Again, they were sized to handle both cooling and ventilation needs of the space. So looking at the air handlers in a little bit more detail, each air handler had a design airflow of just over 13,000 CFM, and approximately 5,200 of that was outside air, which means the customer going with the radiant cooling system, the size of the air handler could have been reduced to handle just that outside air capacity. Not only would this have resulted in a smaller capacity fan and smaller capacity coils, they also would have been able to eliminate the return air fan, mixing dampers, and a lot of controls that go along with that. That smaller air handler was priced, and had the customer gone with the radiant cooling system, they would have seen an additional $50,000 on the project here. And again, there were 2 air handlers on this project. So the total savings on the cooling side of things would have been around $100,000. And additional savings that are not shown on the screen would have come from smaller ductwork. It was estimated that the ductwork could have been about 45% smaller with the reduced CFM. So while there will always be project-specific details that will have to be considered, radiant heating and cooling should really not be considered a solution that's going to cost you more money. And in fact, in many cases, they could result in cost savings, and that's before you turn the system on. So what we just saw were the mechanical savings, but like I said, there are architectural savings as well. The baseboard heaters in this pool take up space, just like the fan coils or cassettes that might be more commonly used in your project. And larger ductwork requires lower ceilings. So had the customer gone with the baseboard heating, when you calculate the width and length of the cabinet, it would have resulted in about 950 square feet of floor area. Now that does not seem like a lot of space, but at $472 per square foot, that comes in at almost $500,000. This is floor space that the owner would not have been able to use, or space that the architect would have been able to exclude from the building to shrink it down. And here are a few pictures of the facility that really show how they were able to fully use that space with clean finishes and being able to push shelves right up against the wall. This level of flexibility really makes an impact on how they're able to use the space to fit their current needs today and whatever their needs may change to in the future. And what architect do you know that does not want higher ceilings? Had the radiant cooling solution been deployed, the ceiling space would have been shrunk by a foot of depth. So when you're working with developers, this is an additional selling feature. And this was a single-story building. But start adding floors, and now we can really have a conversation about shrinking the overall height of that building, which would have a significant savings attached to that. So everything that we saw just then was for the install cost. But now let's look at some savings on the operational side of these systems. So to do that, we're going to look at 3 different school systems. All 3 of these schools have radiant floor heating installed, but 2 of them have radiant cooling. And all 3 of these schools are considered to have a highly efficient design with a very tight envelope. School number 1 had a similar install for the design that we just reviewed, radiant heating, but forced air for cooling and ventilation. School number 2 had radiant heating and cooling and a dedicated outside air unit for ventilation. And school number 3 had radiant heating and cooling and a dedicated outside air unit as well, but made use of displacement ventilation, which is a method of providing lower velocity air at a slightly higher cooling temperature. And here we see the kilowatt per square foot for a calendar year, the same calendar year for these 3 facilities. So essentially the same use, same climate, etc. The top green line is the school that used forced air for cooling and ventilation. And then we see the other 2 schools that used radiant cooling and have pretty significant savings. So just to see that another way, we're looking at about 27% operational savings with a radiant heating and cooling system when compared to essentially the same building using radiant heating but forced air for cooling. And this is the natural gas cost per square foot for each of those buildings. Again, all 3 of these buildings had radiant floor heating, but this slide was left in because there were different strategies in place for heat recovery and delivering the air. And the takeaway here is that there are multiple opportunities for savings when you consider the entire system instead of just the fuel source. And when you consider that installation labor is typically the largest cost in a radiant project, being able to significantly increase the efficiency of installation can help save projects that may be at risk during value engineering exercises. So to help lower the cost of radiant system, radiant rollout maps provide a fast, efficient, consistent method for installing radiant heating and cooling systems in large commercial areas, reducing required manifold ports by more than 60%, wire ties and staples up to 30%, and improving installation time by up to 85%. And when you consider that installation labor, more and more engineers and building owners are coming to understand the benefits of these high mass radiant heating and cooling systems, and we're starting to see them used in applications and very large scale, just like this one. Here we're just under 3 million square feet of radiant heating and cooling in Cupertino, California. And this building was able to integrate that prefabricated solution to really create this state-of-the-art 4-story corporate headquarters. The radiant heating and cooling system was designed to work in conjunction with a natural ventilation strategy that helped the project earn a LEED Platinum rating. To achieve environmental goals, corporate real estate must act now. Decarbonizing buildings offers cost savings, compliance security, and a competitive edge as more investors and tenants become aware of what is going on. According to Forbes magazine, stricter regulations and brown discounts as high as 30% are likely coming in the near future. The truth is, nobody knows what the next great technological breakthrough might be, but we do know that all of those that have been identified and emerging as affordable are adaptable to a hydronic system. So choosing a hydronic system is really the best option for your building now and in the future. So here in our last category of economics, hydronic radiant systems really excel. Now that we have addressed the 5 areas we initially identified at the beginning of our presentation, we can clearly see that hydronics and specifically radiant systems truly can help you achieve your decarbonization goals. Before we wrap up, let's quickly explore some actionable steps that we can take and resources available. So how can we mitigate the impact of embodied and operational carbon in MEP systems? It begins with architects taking the lead. Prioritizing design strategies such as optimizing daylighting and window-to-wall ratios is essential. The goal is to align as closely as possible with passive design principles by upgrading building envelopes. Adopting a less is more philosophy is key in mechanical system design. This means specifying lighter equipment with economies of scale. Studies have even shown that integrating equipment with architectural design, like using a concrete slab with radiant heating and cooling instead of a typical steel structure with VRF units, can reduce whole life carbon emissions by 40% compared to standard all-electric buildings. Addressing refrigerant leakage is paramount due to increasing pollution and temperatures driving greater mechanical cooling demand. It is vital to specify low GWP refrigerants with minimal leakage and ensure 100% refrigerant capture and recovery during decommissioning. Conduct a whole building lifecycle assessment early in the design process and advocate for data transparency by requiring product-specific EPDs throughout design, budgeting, bidding, and procurement. Multiple studies have been done by many independent labs and universities to support the information that has been presented in this presentation. These studies have analyzed buildings across North America in a mix of climate zones from warm, humid 3A to very cold 7A, and they consistently come to similar conclusions. Results suggest strong energy saving potential for radiant systems, even cooling, in the majority of climates, like the one referenced here by the Center for the Built Environment at Cal Berkeley as part of the California Energy Commission EPIC project. This pattern of using radiant systems to accomplish low energy outcomes is also seen by over half of the zero net energy buildings in the New Building Institute's Getting to Zero database. Speaking of CBE, they have great free tools such as the Thermal Comfort Tool. This tool has been online and free since 2013 and is being regularly updated with enhancements to include approved changes to ASHRAE Standard 55. And the Hydronics Industry Alliance is a committee of hydronic equipment manufacturers in North America, organized and run by IAPMO, the International Association of Plumbing and Mechanical Officials. The mission of the Alliance is to educate, integrate, and communicate the advantage of hydronic system solutions. Among the tools provided by the Alliance is BEST, or the Building Efficiency System tool. BEST is another free total commercial building tool that models and compares HVAC systems based on actual system performance data in just minutes for free, saving time and money while pointing the project team in the right direction for their location, energy needs, and budget. And Uponor Academy Online is another great resource where you can find free educational webinars delivered both live and on demand. Uponor, as you all probably know, is the industry leader in polymer piping solutions, but we are heavily involved with several industry associations as well. And this year, we actually launched a new series called the Uponor Academy for Engineers, where we're now offering sessions geared towards our mechanical engineering partners and offering PDHs for those sessions as well. So if you would like to learn more about what we're doing at Uponor, we will also be at AHR in Chicago next month, so please feel free to stop by our booth and talk with our experts. And I do not enjoy ending presentations on a negative note, but truly understanding the reality of our situation is very important right now, and too many people are simply trying to ignore the facts. According to the World Resources Institute, the State of Climate Action 2023 report, global efforts to limit warming to 1.5 degrees Celsius are failing across the board. We are lagging significantly behind the pace and scale that is necessary to address the climate crisis. And an enormous acceleration and effort will be required across all sectors to get on track for 2030. Sadly, it seems the largest barrier to progress is the lack of willingness to change unless being required to do so. We simply need more people to get on board with this initiative. And with that, today's presentation has come to an end. So from myself and everyone at Caleffi and Uponor, thank you for joining us today. I know that was a lot of information and I talked really fast, but I hope you found it useful. If you have any specific questions, I believe we may have a little bit of time for Q&A, but my email address is on the screen, and you're certainly welcome to reach out to me directly, and I hope to see you all at a future presentation.
Thanks, Hailey, and great job. I think that you wrapped it up really well, that there's just an enormous possibility to make an impact with the systems that you're describing here. And like you mentioned, water is not a new transfer media. That if you ask somebody to say, what is the refrigeration that's going to be the one that everybody wants to use, that's required or is allowed in 10 years, I don't know what the answer would be. I think that refrigeration is great for a heat pump, and from the outdoor unit to the indoor unit to get that COP and the additional boost there. But water is just such an excellent way to get the energy around the building. And there are a couple questions that came in related to, and kind of similar questions to what we usually see with radiant cooling, like, well, what about occupancy swings? What about humidity? And you mentioned it as well, the ASHRAE standards 55 and 62.1 and current construction codes, like they're just putting you in place to be successful with these systems. If you have condensation on the floor in a new construction building, you probably wildly broke some of those rules that Uponor didn't establish and Caleffi didn't establish. These are like the rules of the day. And they provide those boundaries to be successful for radiant cooling. So don't be afraid, everybody. We can do this. The examples that you showed, like that city center in Las Vegas, huge occupancy swings, really difficult construction to keep people comfortable, and it works. I walked through that building. It's it's one of the most comfortable buildings in a tricky set of circumstances. So don't be afraid, everybody. We can do it, and we can save a lot of energy. I think is how I would wrap up a couple of those. So let's see. Go ahead.
Every project is always going to have some quirky nuance. So it is important that you're working with a partner that can help you model that in spaces where there's not kind of a vestibule at the door. You may want to consider not putting the piping in the flooring right there, but again, those are models that you can simulate and you can run and you can control it. And in spaces where you have localized levels of high humidity, maybe we put an exhaust fan, but there are tools out there that can help you be able to implement these designs without concerns of condensation.
Yeah.
I think the key that people tend to forget about is that we're operating at higher water temperatures and higher space temperatures. And then, of course, you're still going to have your dedicated outdoor air system bringing in your ventilation and doing some dehumidification for you. So it's important to think of the whole system not just the individual components.
Yeah, well said. And thank you for your time. I'll have you just walk through the last couple slides here, the Caleffi stuff to finish up. And then we'll send everybody on their way and answer any other additional questions that came in after the fact. So
Okay.
here's how you can get a hold of us. So we've got a direct line to tech support, or you can email us and you'll talk to one of the people on the screen here. If you have any questions about a Caleffi product or a system, we can point you in the right direction or get you to a professional like Hailey to take it from there if it's outside of our scope. And then on the next slide, we've got a podcast. This is great for contractors on the way to a job site to hear about the recent calls coming into the tech support lines and see how they can adapt and make systems work efficiently. And then here's where we are on social media. So send us your job site pictures. We love to see what's happening out in the field and post and like and reshare and things like that. And with that, I think we're going to wrap up the slideshow. So thank you again, Hailey. You did a great job. We really appreciate your efforts. Thanks so much for what you do for the industry. And we will see some of you, hopefully a lot of you, in person at AHR in January, and then we'll be back with Coffee with Caleffi at the end of third Thursday of February with Christoph Lohr to do a DHW sizing presentation, which is kind of a part 2 of what we did earlier this year, and that's going to be a good one too. So thank you again, everyone. Have a great day, and we'll see you soon. Bye.
Thanks, Zach.